Okay, so welcome everybody to our first out of two meetups we have for September 2020. So today we have a guest speaker, a special guest speaker, Addison Higham from StreamNative, who is going to talk about Apache Pulsar, which is a very exciting project. I think it's getting increased popularity slowly. So I think it will be very interesting for people that know Kafka to know a bit about this project. But since we are Java.IL, it's not going to be focused solely just on how it works, but also how it looks like from the contributor perspective, like the challenges that the contributors are facing there, and stuff that we as Java developers can learn. Before we start, a couple of administration notes. So just a reminder, Java.IL is the Israeli Java developer community. Our goal is to essentially spread what we call a production knowledge that can help you do your daily work in a much better way. And to do that, we spread the knowledge among us. So it can be a new library that you learned, it can be a new technology, it can be a production use case and a pattern. Just about anything that can help other people do their job better. So we need speakers. So please feel free to come to Chaim, Uri, or me using the meetup message to the admin, and we'll help you sort out any topics that you want to present. Some people have addressed us, but it was August, so many of us were in vacation, so we couldn't address all the CFPs so far, but we hopefully will do it soon. But still, we do need. So that's how we can use your help as a community. And the second thing, for those of you who don't know, we have two social sites. So of course, besides Meetup, so we have the Facebook group that if you haven't joined, I urge you to join. It's a really good place to ask a question, local people, and then it can easily just use your native language or just pick up the phone and talk with someone who use this technology or handle this problem. This is opposed to just asking someone on Stack Overflow and waiting for an answer. So it's really a good place to use for a local forum. So that's the Facebook group. Also, we have the YouTube channel. We always record our talks. Of course, in Zoom, it's even easier and free, but we usually have our own cameraman. And, and now that we have transitioned into Zoom until who knows when, we are using this opportunity to actually increase the participation of top talent from around the world that is involved in many interesting projects. And so if you missed the lectures that we've been doing for the last 6 months, I really urge you to go to our YouTube channel and take a look. Some of them are in Hebrew, so it might be easier, but some are in English. And I think it's very interesting, and we have many lined up also. So keep an eye on the events that we have, and I think it's really interesting and helps you in your day-to-day work. And that's about it. So without further ado, Addison, the mic is yours.
Thank you so much. Appreciate the introduction, and I'm really glad to get a chance to speak to you guys today. I like participating in my local user groups, and glad to be able to be a part of yours half a world away. So let me see here. We'll get started with sharing this. And I have kind of an ultra wide monitor here, so hopefully, does that look good to everybody? Thumbs up from anybody?
Yeah.
Okay, cool. Make sure just that doesn't display weird or something in Zoom. All right, so as mentioned, we're going to talk about Apache Pulsar. And it was also already mentioned, we're going to go a little bit over kind of, probably spend about hopefully half the time talking about kind of Pulsars and its architecture and how it works and some of the features. And then the second half of the talk, a little bit about more into a deep dive in sort of Pulsar internals, some of the design decisions and how those design decisions might benefit you and your applications. And as well as mention some of the challenges that we're kind of still working through and of how we build Pulsar. Definitely, I want to also mention as a kind of a prerequisite. I've worked on Pulsar for about a year, but I am by no means an expert in every aspect of it. It's a large, complex piece of technology that does a lot of things. But if you have any questions, feel free to ask them, and I will do my best to answer them if I don't have the answer, to help get you to a resource that can. So yeah, without further ado, I'll just introduce myself. It was mentioned, my name is Addison Higham. There's my GitHub and Twitter. I'm not super active on Twitter these days, but trying to get more. And so my job, I work at StreamNative, and I'm a software engineer and also sort of play a kind of community manager role. You'll see me a lot in the sort of the Apache Pulsar Slack. I've been a software engineer for about 10 years now, and I was previously a software architect at a company called Instructure. It was an education company, made a product called Canvas, and I did a lot of things on sort of the big data platform there. And my most recent project there before leaving was a Pulsar, and I really fell in love with it, had a lot of fun with it, and decided to make it my next full-time job. And if you want to get a hold of me, ask me questions, the Apache Pulsar Slack is a great place to find me, and we're always happy to have people who have questions or exploring Pulsar join there. And I'll link that at the end of the presentation. So as I already sort of mentioned, we're going to kind of go in over an introduction to Pulsar, some high level of kind of what it is, an example of the API, as well as a look at the architecture and how that architecture enables some unique features. And kind of in the second half of the talk, we'll talk a little bit deeper about Pulsar performance, how it gets the performance that it does, and whatnot. So first off, this is sort of the what is Pulsar? So if you go to the Pulsar homepage, the blurb you'll see at the top here is Apache Pulsar is a cloud-native distributed messaging and streaming platform. So kind of encapsulating what Pulsar is in one sentence is a difficult thing to do, and even perhaps more difficult to unpack. So I'll kind of break that down a little bit. So Apache Pulsar by Cloud Native. Pulsar is designed and intended to be run on kind of elastic cloud environments. And a lot of the usage we're seeing from Pulsar and the adoption we're seeing is because it is well suited to those environments where it has a high degree of scalability and dynamic elasticity. So if you want to add new capacity, it's pretty simple to do that. Similarly, it's distributed, so Pulsar is horizontally scalable. So clients and the data that they're sending are segmented across nodes. With adding more nodes gives you more capacity, and there's no single point of failure in that. Losing one node doesn't bring down the rest of the system. Pulsar is also a messaging system. So I think a lot of people mentioned here, they're familiar with Kafka, have used Kafka before. Kafka's primary API is that append-only log, right? And everything is sort of just relating with that log and then consuming from that log. Pulsar has similar capabilities, but actually its first API, the API that is the most common, is actually more of like a pub sub API. So if you've used a system like RabbitMQ or SQS from AWS, the top level API that you will use most of the time actually takes is a bit more of that sort of flavor, where we publish to a topic and we register a subscriber to that topic, and those messages are exchanged. And we also offer a number of different more messaging topologies if you want to, which I'll get into in a little bit. And then finally is sort of the streaming component. So in addition to allowing Pulsar to act more like a pub subsystem, the internals are in such a way that it's more conceptually similar to Apache Kafka. And so Pulsar also supports a lot of use cases like long-term event storage, stream processing, reader-controlled offsets into a topic, and ordered consumption. So all those things, what we like to, what it's not mentioned here, but one of the ways that we often talk about Pulsar is we call it a unified messaging model. Or sorry, it's not in that on the homepage, but I do have it here. And so that what we would kind of call Pulsar is this next generation stream processing platform that has this unified messaging model that lets you both sort of fit a lot of the use cases that you've maybe traditionally used with RabbitMQ or SQS, as well as some of the features of Kafka combined into a single messaging system. So, and a bit of background and a bit of history. So Pulsar was initially developed at Yahoo, now known as Verizon Media. So if you see we have a lot of content if you'll see a lot of talks and whatnot from Verizon Media. They were kind of the original developers of Pulsar. They open sourced that in 2016, and it became a top-level Apache project in 2018. Yahoo at the time originally developed to help replace a lot of their JMS workloads. And not, it's not necessarily, Pulsar's not there to do everything that JMS can do, but a lot of the core messaging use cases of JMS. And so that means that they have, millions of topics. And they also wanted to, so that a lot of the existing systems they looked at replacing it just really weren't a great fit for as many topics as that they had. And they also wanted to do some things that operationally made it a lot more efficient. So since then, Pulsar has been deployed by a lot of companies. Tencent is a big user of Pulsar in China. Yahoo Japan, that actually is distinct from Yahoo. Yahoo that's now Verizon Media. Yahoo Japan is a big user of Pulsar. Nutanix, as well as the company I was from, Instructure. And there's a lot of other companies that are either using Pulsar already or in the evaluating and adopting Pulsar. And so StreamNative, the company I work for, we were started in 2019, and we were founded by some of the original maintainers of both Pulsar as well as Apache Bookkeeper, which is a dependency of Pulsar, which I'll talk about more. So we have most of a good number of the PMC members and committers in the project, and obviously our job is to help grow and adopt Pulsar and to help companies that are going through that process. So I already talked a little bit about these, but just to kind of give a more complete idea of kind of the features of Pulsar, we already mentioned sort of that unified messaging model. So you get both traditional messaging use cases like PubSub, work queues, as well as some of these more like event stream use cases with long-term event storage in sort of one system. One of the especially from people who are familiar with Kafka, one of the big advantages of Pulsar is that Pulsar has seamless and automatic rebalancing of your cluster. So if you add more capacity to your Pulsar cluster, there's no need to go and run some external process to rebalance your cluster. Rather, that is handled natively inside the cluster, and very rapidly that new capacity can be used. Similarly, for things like failure, if you lose a node, there's not like a big process of rebalancing and replacing that node. Pulsar can have very high throughput and low latency. There's Pulsar clusters that regularly, receive millions of writes per second and do so with very low latencies, with median latencies of like 5 to 10 milliseconds. Pulsar also, one of the main things that it was designed for from the get-go is to be highly durable. So some of the other messaging systems that exist, Kafka, for example, depending on your configuration settings, the defaults may have some chance of message loss. Similarly with like RabbitMQ. Pulsar's defaults are highly durable, and you won't lose any messages. I'll talk a little bit about how it does that. Additionally, Pulsar has a lot of other nice built-in features. Multi-tenancy is built into Pulsar. So when you create a Pulsar cluster, there's a concept of tenants and namespaces, and those are sort of organizational units as well as units of permissions that you can give to users, and then run a single Pulsar cluster that can work for all the different teams in your organization. Pulsar also has built-in geo-replication. So you can allow Pulsar to replicate messages across, for example, the company I was at, Instructure, we replicated across 6 different geographic regions, and that's all allows you to sort of manage your Pulsar cluster as one global cluster that spans different geographic regions. And then one last feature here, but there's many more that I could talk about. Pulsar has built-in tiered storage. So when you after a certain period of time, the messages that you've written can be offloaded onto cloud storage like S3 or Google Cloud Storage, and without any change to the API, the consumers can then consume that data from the backing cloud storage, and you can offload it from your disks, which can really make infinite retention a possibility and actually cost effective. All right, so lots of features there. Let's talk a little bit about like what the kind of the core concepts are of Pulsar. And if as many of you mentioned have used Kafka, some of these will be very familiar to you, but there are some kind of unique differences here. So like most messaging system, there's kind of this idea of a producer and a consumer, and a broker that acts as kind of the intermediary between those two. That also is similar concept within Pulsar. Additionally, we also use sort of a topic-oriented structure, much like other messaging systems. One of the unique things about Pulsar is that it uses, oh, excuse me, I guess I can't highlight, is the URL sort of structure that is used to fully qualify all topics. That takes sort of this form here. So messages belong to a topic. They can contain an arbitrary payload along with some optional parameters like a partition key and metadata that can be used for some additional functionality. And then this is maybe one difference from a lot of, particularly from Kafka, is that in Pulsar, all topics are, a topic only has a single partitioned, whereas a partitioned topic is sort of is composed of many topics underneath the hood. So unlike Kafka, where every topic can have a number of partitions, the topic is sort of the atom in Pulsar, and you can just group multiple of those together to create a partition topic. And then, as I mentioned, there's tenants and namespaces, and these are these hierarchical organizational units that we use to provide multi-tenancy as well as some isolation and security. And so, okay, that's a lot of data. I'll stop for a second. Any questions about that? If anybody has any burning questions in the chat, throw them there. And that actually, throughout this presentation, I'll keep an eye on the chat. But I'll move on.
I have a question. The tenants are separated also on the physical level? Or
they can be. So by default, multiple tenants can share the same machine, but there is also the possibility to isolate tenants to certain resources. So you can then use the same cluster, the same like interface to manage it, and then internally Pulsar will map those tenants to a certain subset of the resources. Yeah, good question.
May I ask a question?
Sure.
Can you explain again, please, about the partition topic, how it goes?
Yeah, so
the previous slide, if you can go back to the previous slide.
I don't know what. There we go.
Yeah.
So a topic only ever is a single partition. So an individual topic always belongs on one individual broker. But Pulsar can have this idea of a partition topic, and that simply is just composed of multiple underlying topics. So if I have a topic called like my topic and I add 5 partitions, then there's going to be 5 actual underlying topics called my partition -0, my partition -1, etc. Wish I had a good visual of that.
Kind of okay, it's kind of different semantics. Like,
yeah, it's very similar conceptually, but sort of the reverse of what you might be familiar with Kafka.
Yeah, thank you.
Yeah, no problem. All right, so we'll talk about subscriptions here, and this is where one of the things that's really important to keep in mind about Pulsar is that the brokers track all of the state and via subscription, and these different subscriptions have different semantics that allow you to map different workloads on top of them. So as is kind of mentioned, this is very similar to a lot of other messaging systems. The subscription is sort of the binding between a topic and a consumer, but these subscriptions have different flavors, and depending on the flavor you choose, you get different behavior. So these are the 4 different subscription types that exist. One of these is exclusive. An exclusive subscription has a guaranteed order, but can only have a single active consumer at a time. So this is most similar to sort of like a single member consumer group that to a single topic a single partition in Kafka. But this allows you to have single consumer bound to a single topic and then get all those messages in a guaranteed order. A failover is very similar. But it acts as they're not both consuming, and one of the consumers is only ever consuming it once, with other consumers being able to be attached to sort of a hot standby. So as soon as this first consumer disconnects, the second consumer can take over and then get that same fully ordered set of messages. Go ahead.
Does that apply also to a partitioned topic?
Yeah, so what happens in a partition topic is that
I'm talking about the failover.
The failover. In both cases, what will happen is that one of these remember, a subscription always is to an individual topic. So what happens with a partition topic is you're going to actually have internally, it's represented as multiple individual subscriptions and consumers, and each one of them will be have its own one of these, right? So if I've got a 5-topic partition, I'm going to have 5 of each consumer, and each one will be bound to its own internal subscription. And then if one of them fails over, it will fall over. If one of them fails, it will fall over to the other one.
So doesn't that require you to have in the air double the amount of consumers for failover?
The consumers, so those are all an internal concept. So when a single machine may, like internally, it's creating 5 distinct consumers, but I only may have two machines that still do that, if that makes sense. This is a little bit of where the way that conceptually they're exactly the same, but internally how it's implemented with a partition topic is to just create 5 of these, but have a single client that manages all of that. So that's all transparently taken care of for you by the Pulsar client.
Thank you.
Yeah, no problem. And then the last 2 types of, and I'm happy to answer some more questions about that later, but the other 2 types of subscriptions are a shared subscription. So a shared subscription has multiple active consumers, but doesn't guarantee you an order. So this is most similar to maybe like a work queue in a good use case for something like a work queue. And then finally, there's a key shared, which is sort of a mix of both of them. This allows for multiple active consumers, but an order is given, but only over a given key. So essentially, each consumer is going to be basically sticky for a given partition key, and they will always receive the same message, or sorry, they will always, all messages with the same key will be routed to the same consumer. And that's really useful for a lot of cases where you may need some order consumption, but you don't necessarily care about a global ordering over the topic, but instead can then split that load off across a number of consumers. And there's actually one other that I didn't oh, I don't know what I did there. There's one other API that's useful here that I did not mention, and that is called the Reader API. And the Reader API basically, whereas all of these, the Pulsar broker is managing the state of where that subscription is, the Reader API allows you to arbitrarily set your offset into the underlying topic. And so that is gives you just full control to kind of build whatever you need if you need to use the Reader API. So we'll talk a little bit about building a client. One of the things that Pulsar, once again, is really designed is to have an intuitive API. I mean, many of you have used Kafka. Kafka or Kinesis, similarly, that they can have some difficulties of kind of learning and understanding APIs, and can be a little tricky to understand everything there. And so Pulsar really tries to have an intuitive API. So this is building a client. As you'll notice here, we have just a single service URL. This is just the Pulsar protocol that we're speaking. I should just mention this is the the binary protocol that's used for sending message. There's an additional API that's for administrative tasks, which for creating new topics and whatnot. And so this is how we send a message in Pulsar. So off a client, we can create a new producer. Pulsar has a full schema registry. For now, we're just going to use a very basic string schema, and we can create a producer for either built-in schemas like strings, numbers, etc., or we can create our own that uses that supports either Avro or JSON messages. As mentioned, we define our topic here, and this topic is a fully qualified topic, meaning that we're specifying our namespace, or excuse me, our tenant, our namespace, and then our topic name. In Pulsar, we can, when we create a producer, we can optionally give it a name. This name has some features in the sense of just, we can know who sent messages, and metadata gets carried along around who sent the message. But this is also can be used for, Pulsar has support for doing deduplicating based on a producer. So if you have the same producer, and it shares a name and it crashes and then reconnects and then sends the same message, the broker can actually deduplicate some of those messages for you. And then Pulsar has both a synchronous and an asynchronous API. The synchronous API, we're sending one message at a time. This is a blocking call, and once it returns, you're guaranteed that message has made it to the broker. Obviously, for more performance, asynchronous can be used, and the additional part about the async API is this can also be used to enable batching, where multiple messages will be batched and then sent along, and that's what allows Pulsar to really, with batching, to really scale to high message rates. It's not shown here, but the send async call returns a completable future that you can just await for that write to be confirmed. Similarly, receiving a message is pretty straightforward. We're going to, off the client, create a new consumer with the same string schema, with the same topic name, and we're also going to give our consumer a name. And the reason for this is this consumer name is going to bind us to this exclusive subscription. So in this case, I am only going to be able to attach a single consumer, which is defined by the name here, and I'm of an exclusive type. And so meaning that this consumer is going to get an ordered view of all these messages. And similarly to the send API, there's both a synchronous and an async API, where we can just call receive, get the message in kind of a loop, and then acknowledge that message, or we can use the asynchronous API and asynchronously acknowledge the message. There is also support for sort of an auto acknowledge, if depending on your use case, but these acknowledgements, generally are what are, unlike Kafka, where checkpointing just sort of happens and whatnot. The use of acknowledgements is important in Pulsar to get proper behavior. Obviously, if you don't send acknowledgements, it will resend certain messages when you reconnect. Okay, any other questions about that? I'm looking in chat here. One question is about throughput. We can talk a little bit about Pulsar versus Kafka in terms of throughput. I'm going to push that into a little later on, though, as I talk a little bit more about that. And the question about should I close the client after the produce, sync or async? Yeah, I mean, once I'm finished with the client, or excuse me, the producer, I'm not going to send any more messages. It's best practice to obviously close those. In both these cases, I'm sort of assuming that you know, we're kind of just running this in an infinite loop. But you don't need to close it after every individual message.
I have a question about
Sure.
maybe the acknowledgement strategy.
Uh-huh.
How do you know? I know that in Kafka, you know, you have different types of acknowledgement for messages. Is that similar in Pulsar?
Yeah, and it actually is based on your subscription type. So for these exclusive subscriptions, we can use a cumulative acknowledgement, where what actually will happen here is periodically these will be batched, and then once it's consumed, you know, the next 100 messages, let's say, it will just acknowledge all 100 messages with one acknowledgement. But some of the other subscriptions, like the shared subscription, that obviously doesn't work as well given the order, and in that case, you actually need to use individual acknowledgements. So depending on your subscription type, there's some semantics of how the acknowledgements work under the hood.
Does it also apply to in a cluster? You didn't get to, you know, fault tolerance in a cluster, you know, acknowledging maybe there's a concept of replication of data. So do you have that semantic as well on the cluster level, not on the consumer level?
Do you mean on the producer side?
Yeah.
So messages are acknowledged by the broker back to the producer. And that's actually, if we're using this in both these APIs, when we're going to, like in the case of the synchronous API, we get an acknowledgement back, and that's when we return out of this blocking API. And similarly with the async API, the return future won't complete until we've received the acknowledgement back. Once again, with this async API, that often is going to involve batching. We'll send a batch of messages, and then we would get back a single batch acknowledgement about all those messages being properly confirmed. And then there's one question here about, is it possible to have multiple exclusive subscribers with different subscription names? Yes. So by creating a different, oh, I actually didn't put that here. By default, if I don't specify a subscription name, but do give a consumer name, it's going to automatically generate a new subscription for every consumer that connects with this exclusive type. With a shared subscription, I obviously want to use the same subscription name. Much as you can kind of see in this document, I can have one topic can have multiple subscriptions of different types defined at any one time. So a single topic can both be delivering to some consumer, you know, multiple exclusive consumers on multiple subscriptions, or, you know, a shared subscription. There's no limitations on the number of subscriptions or the type of subscriptions that you can in parallel have to the same underlying topic.
I think if Ori, I'm not sure that I understood your question correctly, but I think that you try to ask about replication and acknowledgement.
Yes.
So if cross geographical region replication also replicates the acknowledgement, that's what you referred?
Yes.
Okay.
Yeah, so we can talk, as we talk a little about the architecture, you'll see a little bit of the difference of, or if you're also talking about replication of like what in Kafka would be the act count. So Pulsar by default, well, we'll talk about that in this architecture section. I think that will kind of answer your question. But to give you a short answer now is that when you create your namespace, you configure what you want before a broker sends back the acknowledgement. You have the chance to configure what that actually means per namespace of how many acknowledgements you essentially want to wait for. But we'll dive into that a little bit deeper.
Okay, thank you.
Yeah, no problem. So as I sort of alluded to before, Pulsar is made up of a few different components. The first two are probably the most important for our discussion today. This is Pulsar itself, and as well as then Apache Bookkeeper. So the biggest difference about Pulsar as opposed to Kafka or some of these other systems is that the storage of messages is distinct from they're two different layers. So in Pulsar, Pulsar actually, the Pulsar code base itself is stateless, and it uses bookkeepers under the hood to add state on top of it as a dependency. So in Pulsar, the nodes are known as brokers. So when we talk about a Pulsar node, we're going to talk about a broker. And brokers, they handle the things like message routing, dispatch to clients. The clients only ever interact with Pulsar itself, so it handles all the client connections, as well as adds all these features like our multi-tenancy support, geo-replication, tiered storage. All of these things live as part of the Pulsar broker. And as mentioned, earlier, the broker is also what sort of handles this load balancing and repartitioning of data. So that's all functionalities that exist in Pulsar, and then it makes use of Bookkeeper to do some of those things. So topics, and more accurately, bundles of topics. So Pulsar takes basically a ring hash of all of the topics in a given namespace and breaks them into bundles. And so you may have anywhere from 4 bundles, which I think is the default, up to a couple of hundred bundles for very large amounts of topics. And each one of those bundles is sort of the unit that gets scheduled to an individual broker. And so what happens internally is Pulsar will have some bundle that's unassigned for some reason, whether that be due to failure, whether that be due to, I guess that's typically in the case of failure. And then that bundle will get assigned to an individual broker. And then clients, through a process of discovery, will look up which broker owns a given bundle, and then they then communicate directly with that broker. And this also has a cache for recent messages, which I'll talk about a little bit more. Second, and then the other large component of Pulsar is Apache Bookkeeper. And we refer to these nodes as bookies. An individual bookkeeper node is a bookie. And Bookkeeper is actually used for the storing of messages as long as the offset storage for individual subscriptions. So all of the state of your actual messages and subscriptions is stored in Bookkeeper. And messages are stored in a group of ledgers. And so these ledgers, they're sort of the append-only data structure that Pulsar is built atop of. And then when a group of bookies come together to form an ensemble, and an ensemble is responsible for reliably storing an individual ledger. This is also where Bookkeeper also has all the mechanisms for data recovery in the event of a loss of a node. It's called auto recovery. When a when a Bookkeeper node fails, this process notices that it's gone and then re-replicates any ledgers to get back to the replication count that we asked for. And another interesting part about Bookkeeper, which I'll talk a lot more in depth a little bit later, is that it has different pools of disks for both read and write that allows it to have very consistent performance, even under like heavy, your reads aren't going to make your writes get slower, and likewise your write load isn't going to affect your read load. And then both of these components, Pulsar and Bookkeeper, both use Zookeeper as their store of metadata. So this includes things like the bookies store data about ledgers, brokers store a lot of metadata about permissions and policies, load usage and whatnot. And they also then use Zookeeper as sort of the service discovery to discover the other bookies or brokers that may be on the cluster. All right, so that's a lot of data. Let's get into a little bit more. We'll now talk about this from hopefully a more graphical perspective that can help make that a little more clear. So as mentioned, brokers, these are the things that all clients interact with. So producers, consumers, they all talk to an individual broker. And as mentioned, this is going to be what's kind of missing from this graphic is each topic is assigned to one of these brokers. So, you know, in this case, the topic that these producer and consumer using are both talking to broker one. And then from there, all the brokers can talk to basically all of the bookies, and the bookies are actually what's used for storing your individual messages. So when a write comes in from a producer, based on your settings, the broker is going to send a write to all the underlying bookies in parallel. And then once that has been acknowledged by some configurable, maybe all the bookies or some subset of the bookies, that is then when the write is confirmed to the producer. So a little bit to your question about replication is the broker is configured to determine how many bookies it's going to persist to, and how many like acknowledgements we need to get back. And then additionally, as mentioned, Zookeeper is used by both of these systems for storing some metadata. The usage of Zookeeper in Pulsar is actually quite low. You know, it doesn't need to be very high performance in terms of lots of Zookeeper capacity or lots of write. It's primarily metadata, with all of the offsets being stored, the higher update offsets being stored in the bookies themselves. So we talked a little bit about you know, the main roles of these things, and we'll talk a little bit here about how these topics are, how this is actually stored physically on Bookkeeper, and how that works. Well, actually, before I do that, any other questions? Is it possible? Any other questions? All right, if not, I'll kind of keep moving on here with this. I guess I should keep an eye on time. Ooh, sorry. I'll kind of rush through some of this. Messages in Bookkeeper are groups of messages are stored in segments. So an individual topic is composed of multiple segments, and over time, these segments will open and close. And so what happens internally is we're only ever writing to the most recent segment. And this is critical to, and each new segment that's created can choose a new group of bookkeepers to write to. So this is some of the details of what Pulsar looks from a scaling perspective. So let's say a new broker is added. Because of the way that Pulsar can dynamically reassign, and because brokers are stateless, when a new broker is added, we can simply just copy, or excuse me, not copy, but can reassign the ownership of a given partition to a new broker, and it will still communicate with the same underlying state. All that we have to have here is this loses some cache of the most recent messages. Similarly, in the case of a broker failure, we can simply reassign a given partition, being that these are stateless, to a new broker. And at the bookie tier, we also get a high amount of scalability. So as mentioned, these segments, and that's what these little things indicate here, as soon as you add a new bookie, new segments can start being assigned to that new bookie. And over time, particularly if we're going to be like aging out, if we have some trim on our topics, over time, this bookie, the load will even out across those very naturally. And so we don't need to do any sort of rebalancing. As soon as that bookie is joined, it's going to start getting new segments assigned to it and participating. And similarly, in the case of a bookie failure, that's where the auto recovery process kicks in, and then we'll re-replicate any of the replicas of its segments to the other bookie nodes. So once again, I want to get to this other section, but I want to give a quick overview of kind of some of the unique features that this architecture gives us. So because of the segment-based storage, where these segments periodically close and then they're mutable and unchanging, that's what allows us to offload these segments to storage like S3 that makes infinite retention cost effective. So oftentimes what you're going to see in a production book in some Pulsar production clusters is that the bookies may only be storing, a day or maybe 2 days worth of data. And then everything else after that is going to be offloaded onto S3. And I have another diet graphic for that. Similarly, because of all of these small segments, we can have things like Pulsar SQL that in parallel will go and read those segments and allows you to batch read all of your old historical data and get an answer about historical data much quicker. And similarly, we have the multi-tenancy and the storage architecture. That's really all these things kind of come together to allow us to have large Pulsar clusters that can all sort of be managed as one unit, and that is truly like a multi-tenant system. As I mentioned with the tiered storage, we're essentially taking these segments and offloading them to S3, but there's no change of API for the consumers. It's transparent to them. The broker essentially reads these segments into memory and then serves those from memory. And I also mentioned Pulsar SQL. Under the hood, this is basically PrestoDB, if you're familiar with that project, where it can read either from the tiered storage like S3 or from the bookies themselves and have all those read in parallel and rip through all your historical data very quickly and answer questions. All right, as mentioned, any questions about that? There's one question here about how many bookies need to fail in order to lose data. So all of those settings are configurable per namespace about how many bookies your data is replicated to. So if you want to replicate your book, like what I think is very common is you're gonna have choose 3 bookies for every new ensemble, and those 3 bookies, obviously you'd need to lose all 3 of them for your data to be lost. So the data is fully replicated to each of them. And then what we do in the case of where one just is missing, there's a process that goes to make sure if there's like a disagreement, but that only happens in failure scenarios. But for some reason, if you're running on a non-persistent disk, like ephemeral disk, maybe you would want to use 5 bookies, and that's all configurable on a per namespace basis. Additionally, it's configurable. You can actually stripe data across multiple bookies. So there's a lot of flexibility in how you use Bookkeeper. Any other questions? Hopefully that means a good thing. But if I'm losing all of you, we can answer a lot of questions, but we'll get through this next section here of kind of the lessons that might be applicable from Bookkeeper and Pulsar. What are some of the things we can learn from that, in any sort of system? So I think one of the things that's most interesting about Pulsar's architecture and Pulsar's design is its Bookkeeper, disk, and memory management. And that's really one of the keys that allows Pulsar to be as performant as it is, and to be as flexible as it is. But before digging into that, I want to talk a little bit about like Java disk I/O methods, because there's a lot of choices in this space, and all of them kind of have some trade-offs. So we're probably all pretty familiar with sort of the legacy, and not in the sense that they're still very useful, but the Java.IL streams, these stream-based ways that we can interact with files and other I/O operations. They operate on individual bytes, and they have typically a blocking API. And then in newer versions of Java, we now have the new I/O and I/O that are the channels, and these are buffer based, right? Rather than dealing with individual bytes that we exchange to the API, we're dealing with buffers that we're requesting be filled, and then we get a response back with an asynchronous API that has been filled. These have much more performance than Java.IL streams, but they still, they're not like the most efficient you possibly can have, as they still require an extra copy from the kernel into user space. Then, I think more more recent, well, not they've been introduced at the same time, but you know, perhaps more well known now for really high performance I/O in Java is to use memory mapped files via the mapped byte buffer. So in this case, what we actually do is we kind of give a ton of control over to the OS so that we're directly map a space of our memory into the kernel memory. And whenever we just kind of view the file as one big chunk of memory and we go and access that memory, if that misses sort of the page cache of the OS, it will go and read that from disk. So this can have very high performance, but offers less control as the OS kind of is owning all of that. And so those are an overview of kind of the main APIs that exist in Java. And you know, if you're just to look at kind of the benchmarks and you're thinking about a system like Bookkeeper, it seemed like the answer is pretty obvious, right? Like with large blocks on certain SSDs, we're just getting crazy amounts of performance with this memory mapped file approach. And you know, obviously all of them are quite a bit faster than sort of the old Streams API, but still the memory map just you know, from outset seems to be completely dominant. But there's some real problems with this approach. So both once again, this internally is just sort of mapped as a buffer, right? Like the API we get as a developer is just sort of a buffer. And the get and put on that API, those operations in this buffer now become potentially blocking. So if we're trying to get at some section of this file in memory, and we call get, and that section of the file is not in the page cache of the OS, you know, that's now becomes a blocking call, and we don't really have a way to control that. It just sort of happens you know, not randomly, but based on what the OS has sort of decided to do in its page cache. And so similarly, that can happen on put as well. And so flushes to disk all happen sort of in the background, also without the ability to control when they don't happen. We can always force a flush of the mapped byte buffer back to the underlying disk to persist it, but you know, we can't prevent it from doing it when the OS wants to. And then finally, with this technique, the caches are controlled entirely by the OS. So if we know we're going to be if we're going to be doing certain access patterns against that file that would be thrashing the cache, that can end up being a lot more expensive than what you would see in maybe just a very straightforward synthetic benchmark, and can really degrade performance. We don't really get a precise control of what's hot in memory. So for all these reasons, you know, this all kind of comes together, as well as some of the design goals of Bookkeeper, to create a very sort of unique write path of how Bookkeeper is able to get very high throughput and very high performance that also is highly consistent. So, I mean, this is an example towards Kafka. The default write path in Kafka, since it only persists when you have ax set at 1 to just confirm to the whoever the leader is for that partition, that's sort of what's recommended in the Kafka community. It is possible for you to lose those messages if the primary fails before it gets replicated to the follower other Kafka nodes. So one of the design goals of Bookkeeper was to be highly available and to never lose your writes, or to make it very difficult to lose your writes. So a high degree of durability and consistency. Additionally to that, there's really obviously the main access is a fast append to an immutable data structure. And another design goal to really have reads be segmented from your writes. So if we have a big influx of writes, it's not going to impact our read throughput. And additionally, our read throughput, you know, a lot of reads happening at once isn't going to starve our writes. So the way that Pulsar does, or excuse me, Bookkeeper does this is fairly complex, but also extremely robust. So when a write enters Bookkeeper, and this is going to happen for every single Bookkeeper node, right? Like you're making these in parallel from your client. The first thing that happens is that is asynchronously added to an in-memory write cache. So this is, just an in-memory call, not blocking to a disk, and then a blocking like fsync call to a journal. And this journal is its own dedicated disk. So by putting the journal on its own disk and this being the main write path, that's how Bookkeeper segments out its main read and write, is that primarily your writes only have to worry about making it to this journal. And then a background process is periodically going to flush that to your ledger disks. And these ledger disks are primarily for read and large sequential reads. So whereas this journal disk has to have like really high IOPS and somewhat sequential access, the ledger disk has a very different performance characteristic where it does large sequential writes and then large sequential reads, which is much more, maps much better to like slower disks, like spinning hard drives and whatnot. So this technique that Pulsar uses of segmenting the disks, and there's a lot more details here in terms of how the write cache is periodically flushed, as well as the read ahead cache that is in memory read ahead cache. Is really critical to Bookkeeper and therefore Pulsar's performance. As we mentioned, we're kind of low on time here, man. We're a lot to talk about. These write caches are done as using direct memory. So, many of you probably use the JVM a lot, that are familiar with sort of the pain that can be of GC and the cost of object overhead. All of these caches are built using direct memory, where we're getting basically off-heap memory and then managing the life cycle of those cache objects ourselves. With the details of those being that it allows us to kind of avoid a lot of the GC pressure that would be if we did these on heap caches. And we also get a ton of control around what is actually actively being cached, with for example, in the read ahead cache, being much more likely to be very hot, because we know that as somebody is reading through those ledgers, they're very likely, we know what they're going to need next. So takeaways for this, for the average, for everyday applications, is that disk I/O is always hard, and there's always going to be trade-offs, but you can really get creative and use between a combination of caches, potentially different disks, to get very great performance out of the JVM. Many people would say, the JVM is not great for databases, but it continues to be shown that you can really do some impressive things with the JVM if you use it when you really make use of all the facilities it gives you. But once again, it's probably not something you want to implement all yourself. So let's dig into hopefully another topic that maybe we can find some more applicability to a lot of our kind of everyday applications. And that is how Pulsar really is able to get high throughput and low latency. In a messaging application, right, where we really want to be is we want to make sure that we have low end-to-end latency, and particularly for tailing reads. And this is the situation where your consumer is basically right at the edge of your topic, and as soon as a new message gets in, we want to get that to our consumer as fast as possible. That's what really makes these systems like Kafka Kinesis and Pulsar very useful, is that we can have this long-term storage, but also low latency. And Pulsar can offer really impressive end-to-end latencies, with 95 percentiles less than 15 milliseconds and less than 100 milliseconds for 99.9 percentile latencies. And usually that's also with like near saturation of a network link. So we can fully saturate the network of a single box and achieve those latencies. And here, some of the ways we do that is that produced messages can be confirmed with only a majority of the bookies. Also some details on the streaming pull approach we use, more caching, and Pulsar's use of asynchronous I/O. Once again, we're running on time. I'm sorry that I guess I had a little too much content here, but I'll kind of just touch over this and then obviously share these slides. Some of the details about writing to Bookkeeper is that we can only wait for acknowledgements from a subset of those bookkeepers rather than all of them. And what that really does for us is that if we've got, you know, three nodes and one of them is in the middle of a GC pause, we only have to wait for the two fastest ones, which eliminates having to that tail latency while still giving us a high amount of durability. And this is something that we see a lot in modern microservices, particularly ones on Java, written in Java, or Go, that have these, you know, periodic GC pauses. That if you don't design for handling tail latencies, they can become problematic, especially as you do hit, you know, higher loads. And so designing for those from the get-go is really important, I think, in these modern microservice systems, and important to understand. And there's a lot of strategies through, you know, service messages, advanced load balancing algorithms and whatnot to deal with some of that. Another thing that Pulsar does to help minimize latency is the streaming pull approach, where rather than just push or pull, you make a request and say, I'll take up to 1,000 messages, and then the broker will write all those messages to you until that sort of it hits that 1,000 messages it told about, and then the client then has to request again. So that gives us a great combination of a natural back pressure mechanism where the client is sort of dictating how many messages it's going to get, but also with really low latencies, and that we're not like waiting for that initial like long pull that we maybe have seen. And you're seeing this more and more in a lot of systems. You know, gRPC WebSockets, it's important to now take into account some of the needs of throughput and latency and back pressure to make sure that your system doesn't, you know, fall over under load, or that you overload certain systems. Once again, the broker does caching of when a write is written, a new message is written, rather than having the producer need to go, or excuse me, the consumer need to go fetch that from Bookkeeper. It's served from an in-memory cache. And that can be really effective in Pulsar because of this write-through caching approach, where we know there's a high bias towards recent data. And I think that pattern is popping up more and more in a lot of systems, particularly you know, microservices, where this you know, maybe you're still writing to a database, but having a write-through cache where you also write that to in-memory, if there's a bias towards recent data, can be very helpful for performance and latency. And then finally, particularly in Java, you know, making use of async IO is really critical for handling lots of connections and really efficiently using the JVM. You know, luckily these days, I think, you know, most of the main frameworks you might be using all support async, but you really need to kind of design from the get-go to really have your APIs be asynchronous as the kind of the first class citizen. And if making use of those can really bring some really big performance benefits. And finally, I just wanted to talk real quickly about a few of Pulsar's challenges that exists that we deal with as developers. This is actually probably one of the biggest ones, at least from my perspective, is that once again, async is great and offers a ton of performance, but it's still a relatively new API in or a standardized API. You know, we've had lots of different future libraries, as well as a lot of callback-based async APIs, and there's still a lot of fragmentation. And that's something that we're kind of still dealing with, is really to get, you know, some of these systems that we depend on, like Bookkeeper and Zookeeper, a lot of the work was done before completable future, you know, existed. And so there's a lot of work going back through to get everything standardized on that, so we avoid having to sort of translate between these different asynchronous API calling mechanisms. And that's important to us. I mentioned here, you know, Pulsar's cloud native. As we move more towards, you know, things like Kubernetes, containers, a lot of assumptions that we've had about, you know, systems that are running on Metal with dedicated IPs are changing. And, you know, we've had to deal with a number of bugs around when an IP changes, that we, you know, handle that and make sure that the DNS, you know, isn't like too aggressively caching that, or something's hanging onto an IP that then leads to you, you know, trying to talk to the wrong worker once your pod is replaced in a Kubernetes environment. Similarly, you know, containers have their own sort of, a lot of systems in Java particularly, you know, are looking to they want to help you figure out what your heap needs to be, and they look at the system or your thread pools. If you don't know that you're running in a container, that can cause problems, but luckily that's been fixed in the most recent versions. And then I could talk a lot more about some of these things, but you know, obviously Pulsar is designed for multi-tenancy, and that means that we really want to be able to give a good quality of service to all the individual clients. Pulsar right now kind of lets that exist as a API that operators of the cluster can use to you know, set rate limits for producers and consumers. but doing that as your gross usage continues to grow can be difficult. And so one of the things we're looking at is how to do like a distributed rate limiting framework so that you can kind of set those more at a global level and ensure that you're getting the kind of the quality of service you want for all your individual clients who may be using that. And I'll just kind of finish this up by saying, like, if this interests you, there's a lot more to learn about Pulsar. The community is growing very fast. There's a lot more features that we didn't cover. And if you have any interest, I would really encourage you to, at the very least, visit the Pulsar homepage and or join us at the Apache Pulsar Slack community. I think there's like 2,500 people now. I'm there a lot. If you have any questions for me, I'm happy to answer any questions as you kind of explore and evaluate Pulsar. And if you want a ton more information, the Pulsar Summit happened recently. This was our first sort of, it was a virtual conference we did just a couple months ago with a number of topics about use cases and running Pulsar and whatnot. I'd really encourage you to check that out if you're interested in learning more. And then finally, so StreamNative, we're here to help people adopt Pulsar. One of the ways that we just very recently can do that is through StreamNative Cloud. We just launched that a few weeks back. It's a fully managed Pulsar offering. Starts at pretty low prices. And if you're interested in getting started with it, just email me at my email, and I'm happy to get you some credits for a trial. And if you're looking for work, if you're really interested in high performance JVM systems, we also are hiring at StreamNative. So, feel free to reach out to me as well if you're on the search. And with that, man, I did a lot of talking. I think there's some time for questions, and I see there's a few in the chat. I can start with going through these questions in chat. So one here is so the write latency. How's the write latency compared to a broker in Kafka? Very similarly, right? So if you're like walking through that write path again, you're going to send a message. You're going to write a message to the broker, and the broker is going to go right in parallel to all of your bookies, and then as it responds back through, based on your configuration settings of what your ACK quorum is, as soon as those are done, it's going to write back. So that's very similar to if you're running Pulsar with the ACKs equal to all, right? If you're running Kafka with ACKs equal all, you're writing first to the Kafka, the leader Kafka, and then the others followers will see that data and replicate it, but you're not going to confirm back to the client. So it's roughly the same in terms of latency. And oftentimes Pulsar can have better, due to some of its strategies of how it flushes to disk, and its use of the journal, can have better latencies than Kafka for your main write latency. There's a question about the serialization it uses. I'm not completely I'll cover that from a few. If you want to, if I don't cover what you're talking about, just let me know. But the network protocol that Pulsar uses is protobufs. So over the wire, it's using protobufs that you then serialize. And then as far as the message protocol, we support it's mostly Avro based, and then we support so that will take any like sort of POJO in Java and convert that into a message via an Avro schema. And we also support serializing instead to binary Avro. You can also persist to JSON via the JSON Avro support. Is there reactive support for Pulsar? There is. I think there is a few wrappers, particularly in this. I know there's some in Scala that are more kind of that flavor, but it's also fairly easy to build on top of Pulsar because of the like completable future and whatnot support. And I think there's some other community projects that I am not as familiar with. Is there a stop the world scenario like in Kafka Rebalance? No, there is not. Well, okay, I should say not the entire world. When a broker dies, that topic or topic bundle needs to be reassigned to a new broker. So during that period of time, all of the Pulsar clients will intelligently buffer your data. And then as soon as that topic has been reassigned to a new broker, we'll then flush all their data. So during that period of reassignment, which usually lasts just a couple seconds, messages aren't being written, but all of that is taken. That's the only situation where that happens. All the other, if you add new bookie disk, all of those things are transparently handled with like no impact to the client. It's only just this reassignment of topics.
I think they meant if you add more subscribers to the same subscription.
No.
So because in Kafka, when you do that, it has to rebalance how the partitions are sharded across the consumers.
Yeah. Sorry, I see what you're saying. So once again, with the different subscriber APIs, if you're adding, since we sort of really think of them in different use cases, right? Like if you create a new exclusive subscription, there's no impact to any of the other consumers, and there is no sort of that in the exclusive and shared and failover. There is no sort of that big repartition. In the key shared, under the key shared, there is sort of that process, but I'm actually not completely familiar with how that works. That's a relatively new feature in Pulsar, the key shared subscription model. And so I'm not completely familiar with the semantics of what happens when you add a new subscriber to that. But I do believe that it is, repartition of the hash, but it's all handled by the broker as opposed to being, there's no, coordination between the clients. It's all just handled by the broker. Lots of bookies that get replicated messages means very high cost, doesn't it? So much like Kafka, where you're controlling the number of replications, right? In most cases, you're going to replicate to, you're going to have 3 copies of a message in Kafka. That's pretty similar to a bookie. The nicest part about Pulsar in comparison is that we usually end up maintaining less disk overall because of the built-in tiered storage that allows us to offload older messages onto S3. So that's really sort of the way we are sort of suggest that if you're going to be running to really look at the tiered storage, because that can really drastically shrink the amount of disk you need to manage. And additionally, unlike Kafka, where you only have a single tier of disk, because the only thing that needs to be really, really fast for writes is the journal, what we'll often see is much cheaper cost as well, because the journal can be, very small, as small as like 50 gig, really high performance SSD, but then you can use, much more cost efficient, longer storage for all of your ledger data. So you get much more capacity for less, because only a small amount of data is needed for the journal before it's copied to the ledger for long-term storage. So typically Pulsar can also be more cost effective that way. And actually there was an earlier question about what do you need for like performance? That's kind of for similar reasons. You don't necessarily want to use the exact same hardware you would use for Kafka for Pulsar, because when you're designing for Bookkeeper particularly, you want to use a disk strategy where you're not spending an oodle on 2 terabytes of SSD like you might for a really high performance Pulsar or for Kafka cluster. Instead, you may only need 50 gigs of the fastest SSD you can get your hand on, and then 8 terabytes of relatively slow magnetic EBS volumes or something. And likewise, because it's not like with Kafka, one thing is doing everything. If you've got 8 gigs of heap that you're using for 8 gigs and 4 CPUs you're using for your Kafka clusters, it's not like you need to have double that, right? Like you will get similar performance for 4 gigs of heap and 2 CPUs for a broker, and the other half of that for the bookie. You can get roughly the same amount of performance between the two. In fact, in some cases better. Sorry, I'm just going through these at a time. Is there integration with Spark Streaming? I believe we have some support for Spark streaming, but I'm not, I know we have support for, I do know there is a Spark adapter, but I'm not sure of all of its capabilities as far as Spark streaming versus Spark, just normal Spark, batch Spark. Is there native support for message schema version metadata? The schema API that we have in Pulsar has a sort of native idea of compatibility. So we sort of carry on through some message data what schema versions you are using. So I'm not exactly sure the question you're asking, but we do have support for having multiple versions of a schema in flight at the same time and being able to set enforcement so that you can't when you introduce changes that that they're compatible.
I think the question was about how does the schema registry work. So I think people might have not noticed that. I think, I'm not sure Kafka has it, but then Apache Pulsar has a schema registry, right? It's an entity that doesn't exist. I think in Kafka, maybe I'm mistaken.
There is a schema registry in Kafka, and the designs are. I'm not familiar with the design in depth, but the schema registry, the way it works in Pulsar is you can either enforce it just on the client for supported clients, or you can run it on the server that actually validates on the server, and there's trade-offs for both of those. But essentially, what the schema registry has some constraints around saying, I am going to allow adding new fields, but that means that older clients who haven't yet upgraded to the new schema may have a problem. And so it's got a whole there's a whole API for controlling some of what the capabilities are as you evolve your schema. And yeah.
Is it also saved as messages in a ledger, or is it the database backing it?
The schemas themselves are stored actually in Bookkeeper. The schemas are stored in Bookkeeper, and then there's metadata, I believe, attached to every message that references which schema that was produced with. So there is both a schema registry that lets you see kind of the history and the current schema, as well as the messages themselves that have some metadata about their schema that reference that schema store. Increment, assignment, and rebalance. Sorry, Ronan, I'm not sure what that question is. If you wanna.
Which question?
This is by Ronan Levi.
Increment, assignment, and rebalance. Ronan, did you mean the idempotent producer thing? If so, please clarify.
Yeah, we do have idempotent produce that works by producer names, which I can get a little bit more into if people have a lot of curiosity about. There's another question here from Tom about log compaction. There is log compaction supported. It works differently than Kafka, in the sense that what you're going to do with log compaction in Pulsar is that you get a choice of whether, like by default, it doesn't actually the compaction doesn't happen in the same actual topic. Instead, the compaction happens in sort of a different. It's the topic's not necessarily accessible to you directly, but underneath the hood, it uses two distinct ledgers for both the compacted and the non-compacted view. And so what that allows you to do is you actually get to opt in on whether you want to read the compacted view or the non-compacted view. And then you can have some control over what your trim is for the non-compacted view, right? So if you want to say, okay, I want to compact and I want to keep everything for, for forever, but I want to keep my non-compacted view for only 3 months or something, you can configure it in such a way. And you just need to make sure your compaction runs every 3 months so that all that data is always within the kind of the trim horizon. And it's really easy to use. All of the compaction is done just in the broker, so it's just an HTTPI to do it. This question, schema registry, I think we already covered that. There's not a database involved. I mean, there is a database involved in terms of Bookkeeper. Bookkeeper can store some data like that. So the schemas are just stored in Bookkeeper. Regarding async challenges, did you consider using Kotlin, Kotlin coroutines? I mean, Bookkeeper has its, both Pulsar and Bookkeeper, have been around for I think their origins of Pulsar started in like 2015. So I think that was, fairly early days. At this point, I don't think there's a lot of code there, but I think there's definitely been questions about, is there some places that might benefit from something along those lines? But at the moment, it's just pure Java. I will share the slides. I'll share them in this chat in just a minute. The StreamNative's commercial company, can you describe the code contribution model? So we primarily just contribute all of our code. I mean, obviously, other than our hosted offering, all of the commits that we do are into the open source Pulsar that's licensed under Apache 2.0, and most of our work is happening in the community. All the features we're talking about, like tiered storage, all of that is in core open source Pulsar. We don't have any sort of secret sauce that's only available in our distribution. We do have a StreamNative distribution if you are looking for some support, where we will prioritize patches and can help you for our commercial or enterprise support customers. We do have that capability to help you get fixes into your own distribution, but those patches are all released into mainline Pulsar. It's just that for our customers, we can really optimize it and get it out to you really quick and cut you a release. Kind of similar question, StreamNative. StreamNative, 99% of what we do in the open source is all open source. The only exceptions to that is in our hosted model, we have some code that limits you from changing certain settings that could potentially, because there's a high degree of control in Pulsar, we limit you from changing certain settings. And so there's things like that we have is via plugin system that exists kind of in Pulsar, but all of the core Pulsar, it's just open source. There's a comment here about Kafka incremental rebalancing.
Maybe I think the question was, maybe you can share a little bit about how, if you know, how the consumer or the subscription protocol works, especially like when you add a subscriber or you remove a subscriber. I think because it's a pain point in Kafka, that's why the people
totally. Yeah. And so that's one of the things, is that all of the state is managed entirely by the broker. And so, as I mentioned, the three main subscription protocols, like shared, the three primary exclusive, failover, and shared. None of those have any of those worries, because of the fact that like an exclusive, you can only have one subscriber, or you can only have one consumer at a time, right? So with an exclusive consumer, you only ever end up with a single. Man, sorry, my brain. With an exclusive subscription, you can only ever have a single subscriber. So there is no partitioning of sort of that data. And with a shared model, since we don't care so much about ordering, there's no guarantees around ordering. When a new consumer comes onto a shared subscription, it's basically just round robin is what happens in the shared model. As I mentioned, the key shared is that one where there is some more there, that there is a repartitioning of the hash, and once again, that all happens on the broker, and so there's less of everybody having to stop, right? Because the broker, since it controls all that state and is doing all the dispatch, essentially what happens is as soon as that new consumer is connected, it keeps a stable mapping of which hashes have gone to which existing consumers, and there's support in the key shared protocol that lets you define how you want to handle that situation of what is essentially repartitioning of those hash keys. And that's where I said I'm not actually super familiar with. I haven't used that API myself personally a ton, but that is something that is handled by the API in the sense that it gives you some control over how it's going to do that. As I also mentioned, there's also the reader API, which that API gives you basically full control over just seeking to arbitrary offsets. And so for certain systems, like if you're using Flink, for example, if any of you have used Flink with Kafka, that's sort of the API that we can use to just let Flink control all that and then repartition as needed. But if you have a specific use case, would be really a great way to kind of communicate us about this is if you want to join the Pulsar Slack, I'd be happy to either get you the information or help you get in contact with somebody who can answer the questions. And there's one more question here about which versions of the JVM do you support? Currently, I mean, it should work with the broker should work with Java 11 and newer. But the version that we currently like recommend is Java 8. So that's currently where we are, is still on Java 8, and that's one of the things that we hope to do in the next release or two of Pulsar is to also get it to Java 11. Well, and the future, and whatever, if there's a newer LTS by then, but at least Java 11. How do the broker and bookkeeper communicate? Is there deployment best practice for broker bookkeeper to gain the best performance? So the broker and bookkeeper also just communicate over a basically what's a custom protocol over TCP. It's bidirectional communication. It is totally reasonable to place a broker and bookkeeper, especially when you're getting started, onto the same underlying hardware. In fact, that's pretty common, is to just let them be on the same hardware. And then as far as larger production use cases, there's not really any. It's kind of hard to say what's a best practice, but typically what we see is, once again, since you don't bookkeepers, we need to have like a quorum there, so we're going to have 3 of those. But the number of brokers you have is it can be pretty arbitrary. You can start with as small as 1 or 2, but you can go up to as many as 15 or 20 and still have 3 or 5 bookies. And that really depends on if I'm doing a ton of like fan out to a lot of messages, that has a different performance profile as opposed to if I'm just trying to really maximize my write throughput. So depending on kind of what your use case are and your needs, you can have very different deployments of Pulsar, and that is both challenging in the sense that I can't just it's hard to kind of give a one-size-fits-all answer, but it also gives you really great flexibility to kind of tailor your Pulsar deployment to really match your use cases. So once again, whether you're going from anything from super long-term storage with lots of cheap, expensive spinning disk, or whether you're talking about a ton of fan out, there's all different ways we can kind of tune performance to do that. And then the question is, what is one more question about the ordering semantics of the virtual topics. So when we're talking about a partition topic, and by the way, the virtual topics, that's something, but you'll just see that through the docs called partition topics in most cases. So with a partition topic, once again, under the hood, what's going to happen there is that every consumer is if I have 5 partitions and 1 consumer, internally the Pulsar client is gonna consume from each one of those topics. So you still get the same ordering semantics per individual topic, but they're obviously just like with Kafka, there is no ordering guarantee beyond an individual partition, or in our case, an individual topic. So you still get the same ordering guarantees on an individual topic by topic basis. That's one of the details about kind of the details about this incremental rebalance, is that because of that plays a little bit in the role in why exclusive consumers, why we don't need to do a lot of those rebalancing protocols, because they all kind of just happen consumers happen at the topic level. Anything else I can answer for anybody? If you want to talk over voice, that's great too. But I'm happy to answer any other questions.
What is the largest installation that you are aware of Pulsar?
I couldn't. I don't know if I could say for the largest. I don't know how big some of Tencent stuff is, but Verizon Media, aka Yahoo, recently talked about at Pulsar Summit their largest cluster, where they handle in excess of on a single cluster. They handle at peak loads in excess of, I think it's 4 million writes per second, and that's spread across. They didn't talk exactly about how many nodes and whatnot that is, but they have, I think, like 18 different clusters, and their busiest has a peak of over 4 million writes per second, and about 6 million reads per second, and they have a few that are, I think, pretty equally sized. And then there's also a lot of, like I mentioned, Tencent has some fairly large clusters and whatnot. There's a question here about benchmarks. Well, I'll just say Kafka or Confluent recently released some benchmarks that if you search just, you'll probably see some things from Confluent. If you take a look at that benchmark, there's actually the way that they configured the cluster isn't very ideal for the bookkeeper. Like I mentioned, they're not their disk configuration doesn't really match what would make sense for most bookkeeper installations. But if you want to, what I would really recommend is, if you're really interested in benchmarks, we have a tool called the Open Messaging. Well, it's not our tool. There is a tool called the Open Messaging Benchmark that has support for Kafka and Pulsar. And what really is recommended is if you to really understand what your workload looks like. But as I can say, in general, if a lot of the benchmarks that I've seen around, they're all going to have deficiencies one way or the other. In most cases, both systems can get really great equivalent performance. I don't think looking at benchmarks is necessarily the biggest thing that for people that are coming from Kafka, the biggest thing that really I think is attractive is not having to deal with things like rebalancing, to have real multi-tenancy as part of Pulsar, and oftentimes the performance is as good or better, but we tend to focus more on the differences that we can kind of deliver with Pulsar rather than raw numbers. It's really hard to compare without knowing your exact use case. Sorry for the wish-washy answer, but there's a lot of benchmarks around, and I think they can be pretty informative, but best is to understand kind of how it maps to your use case.
I think it's worth mentioning regarding your lecture. You talked about the replication guarantees, and you mentioned the async writing to the write-ahead log in the bookkeeper. I think it's worth mentioning there is a really nice trick there that when it's writing to the write-ahead log, it does so. It doesn't call fsync after it, because of course it will ruin the performance if after every write it will call fsync. So what it does, it calls fsync I think every second or something is configured. So and then it acknowledges back to the broker, which is the bookkeeper client. So in that sense, you get a guarantee that the data was written to disk, as opposed to when you write. I think, someone will correct me if I'm wrong, but I think in Kafka, I'm not sure that when it acts back, it's necessarily f-sync to disk. So
correct.
So it batches the right sync, but you don't lose the ACK. So when it acts, it's actually written to the disk.
Correct. Yeah. So by the time you get an ACK to the client to Pulsar, it has been f-synced to disk. Unlike, and this is one of the things, once again, every system has a different choice, and there's no reason to say one is better than the other. But it is one of those things that depending on your use case, Kafka may not be delivering the durability you're expecting. And that's one of the things that we try and be really clear of, is that if you want lower durability, you can do that, and you can perhaps get some better performance. But in general, the defaults that Pulsar has is very high durability, and you have to kind of opt into anything lower than that.
Does it mean, maybe you can expand on that, does it mean that the read is primarily affected in performance because you have to read now from all the replicas, because some may not have like all the data?
So it basically just can issue the read. And this is actually, that's a good question. I'm not entirely sure how all that works in that level of detail, but the reads from, so most of the time, if you're talking about a tailing read, you're not going to hit the broker or the bookie at all, because as soon as that write, once again, this is the write through cache aspect of the broker. Once it confirms to the bookies, it then stores it in its write through cache, and anybody who's in sort of close, near the edge or at the edge of the messages don't have to go fetch that from Bookkeeper. They're just going to directly get it from memory of the broker. And so that's one of the ways in which, especially if you're in this tailing read scenario, Pulsar can get really, really great performance. And you're really only exercising the write path aspect of brokers. When you're talking about a trailing read, right? These reads, or a catch-up read, excuse me. If you're talking about a catch-up read where you're further behind and it's not in the Pulsar's message cache, and you are going to go be hitting the Bookkeeper, I believe what happens there is that it makes a request to all of them in parallel to get that segment, and then just whichever one is fastest is who it will then read the sequence of entries from. But in that case, you're going to be hitting that from the, if this is like a segment that hasn't been opened for a long time, as soon as you hit that the first time, it's going to open that, and then it's going to start filling that read ahead cache, because we assume you're going to be like scrolling through that whole topic. That's why with the caching strategies than Bookkeeper, we can get really great performance also on those catch-up reads by using that read ahead cache by eagerly loading that read ahead cache. So what you tend to see is that, so it's technically possible, but unlikely that you will need to read writes from the write cache. That doesn't tend to happen very often because of the broker's own in-memory cache. So most of the time, by the time if it's fallen out of the broker's cache, you're hitting it from the read ahead cache instead. But you do have to check the right cache potentially.
I think it's also worth noting a very interesting point that not sure again everybody knows that is that the data is essentially, if you look only on the disk side, I mean the Bookkeeper, which represents the disk for a Bookkeeper, for a Pulsar, the data is essentially always spread across, because what happens when you write data, it chooses like 3 nodes, it writes the data to them, and then after a while, it chooses another 3 nodes, and then another
Correct.
3 nodes, and then another 3 nodes. So the data is always spread across. So there's no like hotspotting, or that enables you to actually really scale up and down the Bookkeeper. So if you have like a sudden peak of load, essentially, given you have, of course, enough partition in your topic, you can, of course, scale the Pulsar because it's effectively stateless. You can scale it up and you can scale it down. And essentially the same for a Bookkeeper. When you scale it up, as opposed to Kafka, from my understanding, of course, you don't have to manage the, say, yeah, this partition must go to this new broker, and you have to manage it manually or write scripts your own. It's completely done for you. And also, it doesn't, when you add a new node, it doesn't immediately start to re-replicate and load balance. Simply joins in and shares the load, and that's it's enables you to actually scale up and down Pulsar, and that's it.
No, great. I appreciate that. Yeah, that's exactly right. That that kind of the flexibility of the way that periodically a new ensemble is chosen is one of the key ways in which Bookkeeper remains scalable by continuing to distribute that load across. And one of the other small things, I just posted this blog post. This is a really great reference if you want to really understand the internals of Pulsar. Is that ensemble size can actually be larger than the quorum size. And so what that allows you to do is to actually stripe your data across more bookies, but for any individual set of entries is only going to be on some subset. So that's actually yet another way in which you can sort of stripe your data across, you get the ability to stripe, and in scenarios where you have maybe a lot of read, you're very skewed towards a lot of like catch-up reads. There's some things you can do there to continue to scale that can make that more optimal, as opposed to fully, that can spread the load across more bookies essentially. So there's actually a lot, and this article that I posted there talks a lot about the things that I talked about today, and it has a lot more nice graphics and whatnot for you. So if you're interested, highly recommend both that blog post. And he also has some really, if you're curious about sort of a comparison of some differences of like a Pulsar and Kafka from a durability perspective and from a fault tolerance perspective, I would recommend you look at some of the blog posts that are on his site, other blog posts there. But anything else I can answer for anybody? Well, if not, then it's been a pleasure to get the chance to speak to you all today. I'd highly encourage you to, if you have any interest in learning more about Pulsar, please join the Slack community. I'll say hi to you there. And once again, if you're also interested in getting started with, if you want to get started with Pulsar and not have to set up your own cluster, feel free to reach out to me. I'll type my email here in the chat one more time. Addison, StreamNative.io. Yeah, as I mentioned, we have a new hosted Pulsar offering. We have all the maintainers and whatnot of Pulsar, and we're happy to help you get started with that, and reach out if you're interested in some credits to try it out. So.
Okay, so Addison, thanks a lot for this lecture. It was really informative. It was really nice to get to know another piece of up-and-coming technology, I would call it. I wouldn't call it new because it's started to been written like 10 years ago, the first piece of line of code, but new to us.
Yeah, and still evolving. So we're very much. I should mention, there's a lot of things that are on our roadmap. One of the things that I will be working on soon is, so we already talked about being to offload storage using the same format. One of the things we'll be looking at doing is like offloading that storage in Parquet data, so then you could read the underlying data in Parquet format for some of these data analytics purposes and whatnot. So there's a lot of interesting things that are still happening in the community, and if you're interested in get involved, we'd love to have you.
Thanks a lot. Thanks a lot. Thanks a lot, everybody. And just a reminder, we have another lecture for September. And this time, this is a local speaker from Yahoo Research Lab. He's going to talk about Oak, which is essentially an off-heap key value map library, which is going to talk a lot about what Addison talked about, which is certain techniques for storing. How did they actually use several techniques to write to off-heap memory, managing it, and how open source system like if I am not mistaken, like HBase have used Oak to try to increase the performance of instead of using the heap, using the off-heap. So very interesting. So that will be happening in September. Check out the meetup page for the exact date and register. Thanks a lot, and see you in that meetup.
Thank you very much, Addison.
Thank you.
Thank you very much.
Bye.